Hello and welcome. In this particular example, we have solved an ideal Rankine cycle problem. We want to expand that solution to tackle more complicated modified cycles. So in that series of videos, here is a problem where we have added the isentropic efficiency of the turbine and pump, and we'd like to see how the solution gets modified because of that. So in this PowerPoint slide, I'm showing the cycle again. The things that have changed now is that the turbine is not isentropic. So therefore, in addition to the isentropic line 1, 2 in the TS diagram, we have 1, 2, 3 for the actual turbine. For the pump, similarly, we have 4 to 5 is the isentropic turbine and 4 to 6 is the actual, 4 to 5 is the isentropic pump and 4 to 6 is the actual pump. One thing to note, however, is that for a liquid, when the temperature doesn't change much, this 4, 5, and 6 will be almost on top of each other on a real TS diagram. Okay, let's go and find out as we solve the problem. So what we'll do is we'll start from the previous solution, we'll open the test code to save time for that ideal Rankine cycle problem, copy the test code, and then we go to the app page, and there we load the test code, Control V, and we can. So this regenerates the solution that we had for an ideal cycle. For instance, if you go to the graphics panel, this is the ideal cycle. You can go to the constant pressure line through state 1 and say state 2. And these two constant pressure lines shows the cycle 1, 2, 3, 4. As I say, 3 and 4 are actually exactly on top of each other because temperature is constant for isentropic pump. Okay, so let's see how we expand the solution now. So state 2 is my isentropic turbine exit state. As you can see, S2 equals S1 and pressure is given. And by the way, if you go to the IO panel and if you isolate the user codes, these are the parameters we entered before. So let's add eta turbine efficiency as 0.9, I believe, and pump equals 0.8. Okay, we can come back and change these efficiencies anytime we want. And you do a calculate, and that pretty quickly solidifies this user input. So we are going to use these as parameters, all these variable as parameters of the problem. So we need to calculate insert state 3, which is the actual turbine exit. So what we can do is that we can click this plus button that clones state 2. So it's exactly isentropic state, same state as state 3, but we want it to be an actual exit state. So entropies are not equal, and the enthalpy can be calculated from the isentropic efficiency formula, which is H3 equals H1 minus eta turbine times H1 minus H2. So we can go to you can just write it down, the definition of an isentropic efficiency, which is the power produced by the actual turbine to the power produced by the isentropic turbine. And you can see the formula I have entered is exactly reflecting that. So once you know how to find H3, state 3 is calculated. If you go to the graphics panel, state 3 should be slightly to the right of state 2 as we expect. So that's correct. Okay, and state 4, nothing has changed. State 4 is still the condenser exit state. Pressure is known and X4 equals 0, which is saturated liquid condition. State 5 is the isentropic pump exit. As you can see, S5 equals S4. So we need to introduce a state 6. Again, we'll clone this state and then say it's not isentropic, except the enthalpy will be determined by the pump efficiency. So we write down the formula for H6, again using the definition of pump efficiency, it will be H4 plus H5 minus H4, which is isentropic turbine pump divided by eta pump. So now state 6 is also known. In the graphics panel, as I said, all these states 4, 5, 6 are on top of each other, but otherwise, as you can see, if we draw the constant pressure lines, it should look very similar. And if you draw another constant pressure line through state 2 or 3, it should pass over 2 and 3. Now, let's go to the device panel and correct, because remember, this is our old solution. So device 1 was the turbine going from 1 to 2, the isentropic turbine, but now it's going from 1 to 3, the actual turbine. So the turbine work will be reduced from 16165 to say 14871. Let's go to device 2, which is the condenser going from 3 to 4. So condenser, the heat transfer in the condenser is found. Device 3 is the pump. It goes from 4 to 6 is the actual pump. And finally, device 4 takes you, is the boiler. It goes from 6 back to 1. Calculate. So if all the states have been calculated, all the devices have been calculated, the cycle is complete, as you can shown here. You can press a calculator if you want, but the first thing to check is that is my w.net equals q.net. That must be, q.net. This is here. They must be equal. Also, now you know what the efficiency is. Everything is spelled out for us here. Thermal efficiency is this. Now suppose we want to do a parametric study. We want to know what will happen if, for instance, the pump efficiency is 100%. So for that, let's remember what the current efficiency is. Thermal efficiency is 37.57. I'm writing it down so that we can compare that. So we come to the I/O panel, and by the way, it's always a good idea to click a super calculate button to make sure all the states are updated and the answer hasn't changed, 37.57. Now if you come to the I/O panel and say, let's isolate the user code by clicking show user codes, and say pump efficiency is 100%, which is 1.0. First we have to do a calculate so that it's registered. So pump efficiency has been picked up here. And now if we do a super calculate, go to the cycle panel, 37.59. It was 37.58 before. As you can see, the efficiency barely changed. So pump efficiency really doesn't change the cycle efficiency as much. It doesn't affect, because pump really consumes a very little bit of power. If you notice, the pumping power W.in was only 40 kilowatt, whereas the turbine power was 14.8 megawatt, 1,000-fold more, almost. So we go and let's take a look at how the turbine efficiency affects. So it's going from 90% to 100%, and remember it was 37.59 before, so we do a calculate here and super calculate, and you will see a big improvement, 41.77. So from 37.59 it went to 41.77, almost a jump up 3 percentage points. So that shows the cycle efficiency is sensitive to the turbine efficiency. Just like we have done a parametric study on isentropic efficiencies, you can imagine you can change any of these parameter, and the way the problem has been laid out, and all you have to do is to click calculate and super calculate, and you will get their effect on the cycle variables. We'll continue to build upon that and solve even more complex problem using this solution.